Hello everyone. In the previous session, we studied about the three frequency bands of common source amplifier. So now in this session, we'll study about high frequency response of common source amplifier. So this is the equivalent circuit for common source amplifier. So to understand how to draw this, let's look into the circuit diagram of common source amplifier. So this is the circuit diagram of common source amplifier. Here, V sig and R sig is there at the input side, V signal and R signal. So we have it here also. All the capacitors, coupling capacitor CC1, CC2, and the capacitor, source capacitor is short circuited. So there's short circuited here. And next, RD, the DC sources are grounded. So this will be grounded. So RD is connected to ground. RL also you can see here, and S is around. This current source is also short circuited and is connected. This VSS is also grounded, so this source terminal is directly connected to ground. And now I hope you are clear about this part and this part, along with this source being grounded. Next, what we have is this is the circuit diagram which is present internal to the MOSFET. So if you go back to my previous videos, we had studied about MOSFET internal capacitors, isn't it? So in that we have seen that there is a capacitance between capacitor present between the gate and the source, that is CGS, across which the input signal VGS will be present. And next, there will be a capacitor present between gate and the drain, that is CGD. Okay, it is present between gate and drain, isn't it? Next, this capacitance that is present between capacitor, whether it is present between gate, drain, and the source, can be neglected because it does not have much effect on the frequency response. So this is about the equivalent circuit of the CS amplifier. Next, let us look into the output side here. Okay, the load current is given by GM into VGS minus ID. This GM into VGS is nothing but the output current of the MOSFET, what are we getting out from the MOSFET. And this IGD is the current that is flowing through a very small capacitor CGD. So the output current is given by the equation equal to GM into VGS minus IGD. So this equivalent model is very complex, isn't it? So we can simplify it further also. So let's see how. These three capacitances you can see here, R0, RD, and RL, they are connected in parallel, isn't it? So these three can be replaced by one single resistor, that is RL dash, which is a parallel combination of the three. Okay, and next we have resistances R signal and RG, that is in parallel. So instead of these two resistors, we can use one resistor, that is R signal dash, which is equal to the parallel combination of R signal and RG. Okay, so next let's see how the circuit gets simplified. So see here, this was the actual equivalent circuit. This was the actual equivalent circuit. See here, these three resistances are replaced by a single resistor RL dash. Okay, rest of it is present as it is, GM into VGS. Okay, CGD. Next, CGS capacitor is also present. Next, these two resistors are in parallel. Instead of these two, we can use only one, that is R signal dash, which is equal to parallel combination of R signal and RG. So that is present over here. So next here, this will be equal to, input signal will then be equal to RG by RG plus R signal into V signal. Okay. And next, this CGT is like a bridge between the input part and the output part of the circuit, isn't it? Now this CGT can also be replaced by a equivalent capacitor that is equal to C equivalent by using the concept of Miller's theorem. Okay, so from Miller's theorem, we know that this C equivalent capacitance is equal to 1 plus gain into the value of the capacitor. So how do we calculate the gain? This gain AV is equal to output voltage by input voltage. Output voltage is see here. Output voltage is equal to, see here, current into resistance, isn't it? Voltage is the product of current and the resistance. So the current here at the output side is equal to GM into VGS. Okay, and the resistor here is RL dash. So output voltage, considering this direction of the current flow, output voltage will be equal to minus GM into VGS into RL dash. This GM to VGS into RL dash along with the minus in considering the direction of the flow of the current. And the input signal here is VGS. Okay, by VGS. So VGS in the numerator and denominator will get cancelled. Okay. So AV will be equal to minus GM into RL dash. So substitute in this equation. C equivalent is equal to 1 plus AV into C. Substitute the voltage gain as GM into RL dash. We'll consider only the magnitude. Okay. So it will be, and the capacitor that we are replacing here is this CGT, isn't it? So CGT. So C equivalent is equal to so much. So see here. If CGT were present, this is the equivalent model. Now, if I am replacing this CGT by equivalent capacitor, that will be present over here. Okay. So now there is no connection between input part and the output part of the equivalent model. Okay. So this CGS along with C equivalent circuit will form the input capacitance to the circuitry. So since these two are connected in parallel, the equivalent capacitor, how do we calculate if the capacitors are connected in parallel? It is the sum of the two capacitances, isn't it? So C in will be equal to CGS plus C equivalent. C equivalent we have found here, that is equal to 1 by GM RL dash into CGT. So substitute it. So C in we got now. Next, R signal. See here. R signal is here, which is the parallel combination of R signal and RG, isn't it? Write that. That is at the input side. Next, by considering the input circuit as a simple time constant circuit, tau is equal to R into C, which is equal to, R is nothing but the R signal dash resistance that is present over here into the capacitance is C in. C in. Okay. Substitute R signal dash for R and C in for C. Next, this omega H, meaning H for high frequency. Omega H is equal to 2 pi F, isn't it? Omega is equal to 2 pi F. Omega H will be equal to 2 pi F H. This is also the reciprocal of 1 by tau. that is equal to 1 by R signal dash into Cin. Now fH will be equal to omega h by 2 pi. Substitute whatever we have got for omega h here, and we'll get fH is equal to 1 by 2 pi R signal into Cn. So let's summarize what we did. This is the equivalent model. I have explained how we write it from the circuit of the common source amplifier. So considering this common source amplifier configuration, we'll write the equivalent circuit here, and then these three resistances in the output side is reduced to RL dash single resistor, and the resistor RC and RG that are in parallel is replaced by one single resistor, that is R signal dash, and the equivalent model will be reduced to so much. And then this CGD is like a bridge between the input part and the output part. So now this capacitance is replaced by equivalent capacitance by using the concept of Miller's theorem. So we'll get this diagram. Okay, the equivalent model is reduced to this model, and here Cin is the combination of CGS and C equivalent. This is how we found out voltage gain V0 by Vin and substituted in this C equivalent capacitance in order to find the value of it. And then Cn, we know that it is the sum of the capacitances connected in parallel. Okay, R signal dash also, from that figure 2 we wrote this. All these things are easy to remember. Only thing that you have to remember is here. Tau is equal to RC, omega h is equal to 1 by tau, and from this we'll find out fH is equal to omega h by 2 pi, which gives us this equation for high cutoff frequency. So in high frequency response, we are required to find this high cutoff frequency fH. Next, we have a problem to solve, wherein common source amplifier having internal resistance R signal of 100 kilo ohm and RG of 4.7 mega ohm, RD and RL is equal to 15 kilo ohm, GM is equal to 1 milliampere per volt, R0 is equal to 150 kilo ohm, CGS is equal to 1 picofarad, and CGD is also equal to 1.4 picofarad. So all the equations are available here. AM is equal to minus RG by RG plus R signal into GM into RL dash. Just substitute all the values and we'll come to know that AM is equal to minus 6.77. This RL dash is a parallel combination of all the three resistances R0, RD and RL. So first we need to find out RL dash and then substitute in this and then calculate the value for midband gain. Next, C equivalent. You know this C equivalent is equal to 1 plus GM into RL dash into CGD. CGD is given. GM is also given. RL dash is found out here. Substitute and we found that C equivalent is equal to 3.2625 picofarad. And Cn is the sum of C equivalent and CGS because they are connected in parallel. C equivalent Cin is found out by the sum of the capacitances connected in parallel, that is C equivalent and CGS. So C equivalent is found out here, CGS is given in the data, so in the problem itself. So we found out that it is equal to 4.256 picofarad and fH is equal to 1 by 2 pi R signal dash into Cin. Substitute all the parameters that we have found. Cin is found out. R signal dash is the parallel combination of R signal and RG. Both of these are given. First find out R signal dash and then substitute in this. And substitute for pi as 3.14. And we found that fH is equal to 381.90 kilohertz. So this is a sample problem on the concept of high frequency response of CS amplifier. It's just substitution and calculation. It's easy. In the next session, we'll study about the low frequency response. So this is all about the high frequency response.